Hi everyone, welcome to the video on continuous random variables, and in this video I'm going to go over just how to solve probabilities with continuous variables, and we're going to be using the calculator a fair bit as well, so we'll see how all of that goes. Now when we're working with continuous random variables, there are two things that we need to basically be able to confirm, and the first is that f of x is greater than or equal to 0 for all of x, so the graph should always be above the x-axis. That's because f of x in this case is the probability, and we can't have negative probabilities. So it should always be above the x-axis, and also that the integral between negative infinity and infinity of the function is equal to 1. Now that's probably a little bit weird and a bit different to what we're used to seeing. We don't normally have to do that, but and we won't always have to go all the way to negative infinity and positive infinity, and you will see why shortly. The other thing I'm going to mention about continuous random variables is that the probability of x equaling some number, we'll call it x, is actually equal to 0. Now this is because we're dealing with continuous events here, so these are events where we can always achieve that higher degree of accuracy. So the probability of getting one individual value, for example 3, is going to be 0 because we could alternatively have 3.000000001, or we could have 2.999999999 and so on. And they would be infinitely close to 3, but they wouldn't actually be 3. So that's the reason that we have a probability of 0. Basically, there's an infinite number of options. So in this question here, show that f of x equals all that mess where x is between 0 and 1 is a probability density function. Now it's also got this part here, 0 when x is less than 0 or x is greater than 1. So that's actually defining it for the entire domain of negative infinity to infinity. We've got these sections here as well as this other section, and well, another way you might see this written is 0 where you just say 0 otherwise, rather than writing it like that. Both ways are acceptable. So first thing I'm going to do is I'm going to sketch this. Now 4/3 times 1 minus x cubed, well this has an x-intercept at 1 and it's going to be a point of inflection. So I'm just going to put 1 there. That's the point of inflection, and if we calculate the y-intercept for this, it should be 4/3. I should be labeling these with their coordinates, but I'm just being a little bit lazy here. I'm just doing this to get an idea of what the graph actually looks like. And that's a negative x cubed, so it's going to come down like that, not going below the x-axis there obviously. And we've got the endpoints there and just there as well, which should be completely coloured in. So that's the first thing. We can see that the graph is always above the x-axis, so that's our first test done. Okay, we've satisfied that one. Now I need to do this other part. And, I should also say that, really we should be sketching a line also along the x-axis for these other parts. But it's just, in this question, this is the only part of the graph that we're really interested in. So now I need to confirm that the integral between negative infinity and infinity is equal to 1. Well, I don't need to go all the way to infinity because it's just 0 all the rest of the way along here, and so there's not going to be any area under the graph. And likewise out here, there's not going to be any area under the graph because it's just running along the x-axis. So all I need to do is the integral between 0 and 1 of our function. And, well, I might actually just write that into the calculator. So I've already done it just here, and you can see that we've got the integral between 0 and 1 of that, and it is equal to 1. So it's equal to 1, and so therefore this is a probability density function. I'm just going to call it PDF. Now I do have another part to this question, but I might just leave that for now, and we'll pick it up in the next video and then get on to another example. So I'll see you then.